with one of the constituents of the proton. So here's my proton zipping along the other direction. So it hits one of the point light, one of the small constituents. In fact, I've made this too big because really these are point light as far as we can resolve constituents. Knocks that out. This point light constituent has got the name of a quark. It was coming in along with the rest of the proton, gets deflected, knocks that quark out, and then the remnant of the proton goes on its merry way. Now, the quarks are strongly interacting. Particles. And by strongly, I mean interacting with the strong nuclear force. So these are objects which have been, which are sitting inside the proton and inside the neutron. Just imagine being a proton for another minute. So you're a proton, you're zipping along this beam line. You get enormously Lorentz contracted because you've been accelerated to very high energy. And so what you actually have is basically a flattened pancake. The whole thing is Lorentz contracted. So you've got this flattened pancake of proton moving along your beam line. The electron comes along the opposite direction. Very high energy, very small wavelength probe. The whole rest of the proton goes on its merry way, but the quark that happens to be interacting with just gets booted out of the proton. The rest of the proton goes on its merry way, suddenly realizes that it's a quark short, and all sorts of messy things happen. And so what you get, in fact, is instead of a proton over here, is the energy and the momentum of that proton gets changed into lots of strongly interacting particles. And I'm going to make a case to you today, and tomorrow as well, that these strongly interacting particles are made themselves of quarks. Or antiquarks. Now similarly, this quark that's been booted out of the proton does all the things as well. It does everything you might expect. These quarks are not, although they are components of these of the proton and neutron, they're not observed on their own. We don't observe any free quarks in nature. It's never been observed. People look very hard. What you do observe, whenever you kick a proton very hard like this, is not the quark by itself, but you find, again, with this stuff, along the direction that the quark has been kicked, you find another collection of other strongly interacting particles. So those are things like proton, neutron, high particle, some of the things that we've met already. So this is a little bit non-intuitive, and if it sounds odd, don't worry. Think about it for a while. You take a proton, you kick it hard, and what you get out, you might expect would be a bit of a proton, but what you actually get out is lots of other strongly interacting particles being kicked in the direction of that quark. That sounds a little bit incredible, a little bit odd. But remember, there's lots of energy available here. Energy be converted into mass, and that's precisely what we've got going on here. Lots of particles and antiparticles are flowing in the direction of the momentum of the particles that were outgoing from these original interactions. You might not believe me. You would be right to question my judgment on this, so let's have a look. This is an example of such an event. This is the result of a collision between an electron and a proton in the Zeus experiment at Hera. Zeus was the father of Hera, I think, and also his wife. So the proton has been coming along this way, and the electron has been coming in this way. And what you can see, so the electron has come in, there's been a collision that's occurred here, somewhere in the middle of the beam pipe, and the electron has been scattered back up here. And you can see this yellow deposit is the energy deposit. It's left in an electromagnetic calorimeter. The electron has created showers, deposited this energy there, so it's bounced off and come back up again. Now, the proton has come along like so. A quark has been kicked hard out of this proton, and this debris, this collection of strongly interacting particles, has made its way along this direction. You can see the stream, it's called a jet often, strongly interacting particles, deposited a little bit of energy in this electromagnetic calorimeter, deposited a lot of energy in a hadronic calorimeter beyond that. So that's what you can see here. There are also some yellow bits of display here. Ideas? Right, yeah, exactly. So these are the proton elements. Exactly. And you can see here's a display in the transverse direction, the electron and the hadrons. So hadrons means strongly interacting particles. We'll come back to give the full nomenclature very shortly. Okay, that's deep inelastic scattering. So before we talk very much more about the evidence for all of these different particles, let's just go through the zoology of them. Let's have them all written down so that we know what they are. You should have a handout in front of you. For points of discussion, I will put them up on the board as well. So the matter particles are the quarks and the leptons. Now later, we will convince ourselves that there are in fact 6 of these quarks. 2 of them are relatively, I'm doing them in a different order. Should I do them in the same order as I have? Let's start. You get start with electrons. There are also 6 of those. The leptons means light particles. Great. Not all of them are very light, but the first ones to be discovered were light, and hence they were given this name. Bit of a historical name. You will probably already have met some of these. So they come in 3 what are called generations. And the first generation should be very familiar to you. It consists of the electron and the electron neutrino. They have electric charge -1 in units where the proton has got charge +1, and the neutrino has got no electric charge, and the mass in MeV on your sheet I've given you is 0.5 0.1 for the electron and is less than 1 electron volt for the neutrino. The neutrinos are very light particles. Measuring their masses are very difficult, in fact, mostly for that reason. And so, at the moment, the best that one can say is put a limit on the masses of these neutrinos. In fact, the best limit on the mass of the neutrino comes from the density of states from beta decays. So you've done the calculation before to the density of states from beta decays. That density of states, and that density of states you probably assumed that the neutrino was massless. You would have got a slightly different answer had you put a mass in there. And by looking at the difference between those plots, you can work out this distribution, what the mass of the neutrino could possibly be. At the moment, we haven't observed any absolute scale for the mass of the neutrino, but it's less than an electron volt. This is all fine and dandy. You think to yourself, this is great. This is all I need in order to have my electrons around my atoms. The neutrino is all I need for beta decay. What's odd is that there is both a second and a third copy of this structure. The second copy has got a particle which is very much like the electron, but is about 200 times heavier. It's got the same charge, but it's got mass of 105 mega electron volts. And it also has a neutrino associated with it, a so-called muon neutrino, which is rather like the electron neutrino. It's got mass of 0, charge of 0, and mass of less than 1 electron volt as well. So there's a sort of pair of these particles. They come together. And there's got 1, 2, 3, 4 particles, and then there's another copy again. Nature is wonderful in her bindiness, and she will give us another copy of this. Tau, charge minus 1, a tau neutrino, mass 0, charge 0, and the mass of this is 1777 MeV, and again, less than 1 electron volt. It is worth asking the question, why are there 3 generations of this stuff? It's worth asking the question, I can't give you a good answer. You will have seen in various places in physics that patterns, repetitions, are often indications of some sort of underlying structure. Think back to the periodic table. So the periodic table has got patterns in it, and those patterns that Mendeleev put together, and others, were an indication as to the structure of the electrons inside the atomic orbitals. Now, it may be that this pattern of repetition that we see here is an indication of some substructure, of some underlying theory, of some underlying principle, which is responsible for it. But no one has yet been able to put together that theory, and no one has yet been able to come up with a very convincing argument as to why there should be 3 of these generations. That's where we stand. Okay, so these are the leptons. The quarks, and the quarks are